So this is the 30th video on rigid body kinematics. So this also I'll take up some more problems on pure rolling from acceleration point of view. Okay. So you must go through this example very carefully. If you understand it fully, you don't have to go anywhere else. You don't have to go any costly coaching institute. Nor do you have to go through any other detailed theory of any other book. You don't have to go through. If you understand this fully, it's sufficient. You just solve problems from wherever you want. Okay. And if you have any doubt, you just write down in the comment box. I'll clarify it. Okay. I'll write down the problem. So question is this. A circular drum with center at C and radius R rolls without slip over a fixed horizontal surface and its center moves at a constant speed v with respect to ground, g for ground, in rightward direction. Okay, fine. At the given instant, P1, P2 and P3 are the material points of the drum situated on its circumference. I have to determine what I have to determine. I'll tell you. Find first radius of curvature of the trajectory. Radius of curvature of the trajectory of points P1, P2 and P3 in terms of R. And theta. Theta is for P3 only. And second, find the tangential acceleration of points P1, P2 and P3. Okay. So these two things we have to determine. Okay, fine. I'll rub this one. See, first what I'll do, I'll draw the diagram of the situation. This is the side view of the drum. C is the center of the drum. R is the radius of the drum. Center is moving at a constant speed v with respect to ground towards right. The drum is undergoing pure rolling here. Drum is undergoing pure rolling over the surface, fixed surface. P1 is the highest point of the drum at a certain instant. P2 is the point of the circumference of the drum at same horizontal level as center. And fourth, P3 is the point on circumference of the drum which makes an angle of theta with the upward vertical. Fine, alright. Okay, tangential acceleration of P1 P2 is to be in terms of V square by R, and this should be in terms of V square by R and theta. Okay, fine. So now, first one, we have to find the radius of curvature of trajectory of the points P1, P2 and P3 at the given instant. For first we determine P1, okay. Now how do we proceed? That is the main question. How do we proceed is the main question, okay. So what we do, we find the acceleration of P1 in two different ways and equate them, okay. So what I'll do for P1, just observe. We apply SRC procedure for acceleration between A, C and P3 in ground frame. Part B, first I'll do this, okay. This I'll rub it, okay. So, SP arrow C, OP arrow P1. I draw the line joining SP and OP. That is the line CP1, which is vertical at the given instant. I give the acceleration of selected point C to P1. But C, with respect to ground, C moves at a constant speed V along straight line. So acceleration of C with respect to ground is 0. So acceleration of C with respect to ground is 0. So I give 0 to P1. That is, do not give anything. That's finished. Now write down the sentence. Or one more thing. At this instant, since it is undergoing pure rolling and center is moving rightward, so omega should be in clockwise sense. Okay. Now what I do, I write down the sentence. P1 moves in a clockwise circle because omega is clockwise. P1 moves in a clockwise circle with center at C and radius R. So I give acceleration omega square R to P1 towards C and R beta to P1 towards rightward direction. Now we must know beta also. Now we know that beta is how much? D omega by dt. Alright. And you know from pure rolling criteria that V is equal to R omega. But V is given to be constant. Radius is constant. So this implies omega is also constant. This implies beta becomes 0. So this term also drops out. So we are only left with P1. So acceleration of P1 with respect to ground is omega square R. Okay. Acceleration of P1 with respect to ground is what? Omega square R in downward direction. Okay. Now what we do? We write down the expression for P1, A P1G in another way. How do we do that? Now you must recall in rigid body kinematics related to velocity equation of rotating rigid body, it was discussed that this point P1, any point on the circumference of the drum which rolls without slip over a fixed surface and center moves at a constant speed, all points on the circumference of the drum move in a cycloidal path. So if I draw the trajectory of point P1, approximate path of P1 with respect to ground, path meaning trajectory, it is something like this. This is a cycloidal path of P1. At the instant shown, P1 is at this point. Okay. Now radius of curvature of the curve of at this point is ρ1, which we have to determine. Okay. Now see, this P1 is moving along the cycloidal path. So it has some tangential acceleration, it has some normal acceleration. Okay, fine. Now see, first we determine AT1. What is AT1? AT1 is the tangential acceleration of P1. And what is AN1? AN1 is the normal acceleration of P1. Okay. Now see, what is AT1? D by dt of V1. V1 is the speed of P1. Now we know if we apply SRC procedure for velocity between C and P1, then what will V1 will be? V plus R omega. If we apply SRC procedure for velocity between C and P1, we take C as the selected point, P1 as the other point. I draw the line joining C and P1. I give the velocity V of C to P1, to V rightward. Then P1 moves in a clockwise circle with C as center and radius R omega rightward. So net velocity becomes V1 plus R omega. But R omega is just equal to V from pure rolling criteria. This also becomes V. So V plus V becomes 2V. But it is given that V is constant. V is constant, so 2V is also constant. So V1 becomes what? 0. This term goes away. Fine. Alright. Is it clear? So V1 is constant. So tangential acceleration AT1, which is derivative of V1, that also vanishes. That goes away. Alright. So tangential acceleration of P1 becomes 0. Alright, fine. Now, what is the normal acceleration of P1? 2V whole square by rho 1 in downward direction. So normal acceleration of P1 becomes velocity square by radius of curvature. Velocity is how much? 2V. 2V whole square by rho 1. This is in downward direction. And since AT1 is 0, so this is also the total acceleration of P1. So these two are same. So we equate both of them. So if we equate both of them, what do we get? Omega square R is just equal to 4V square by rho 1. This we can say. Alright. Fine. Now omega is how much? Omega is V by R. So omega becomes V by R. So we can write omega here. V square by R square into R becomes what? 4V square by rho 1. V square cancels out. 1 R cancels out. So rho 1 becomes how much? 4R. One answer has been obtained. Fine. So rho 1 becomes 4R. One answer. And tangential acceleration of P1 becomes what? 0. So one more part of question has been answered. AT1 is 0. One answer has been fully obtained. Alright, fine. So radius of curvature of the path of P1 at this instant is how much? 4R. And tangential acceleration of P1 is what? 0. So one answer has been obtained for both parts of the question. Alright. So this I'll rub it now. So now we have to determine the radius of curvature of the path at point P2 and also the tangential acceleration of P2. That we have to determine. Okay, fine. Tangential acceleration of point P2, that has to be determined. Okay. So in part of the second part of the question, let rho 2 be the radius of curvature of the curve at P2. Radius of curvature of trajectory of P2. So this rho 2 we have to determine. Okay. Again, what we'll do? We'll find the acceleration of point P2 with respect to ground by two different methods and equate them. Equate them along which direction? Along the common normal. Okay, as I demonstrated just now. So, what I do, first apply SRC procedure for acceleration between C and P2 in ground frame. SRC procedure for acceleration to between C and P2. Between C and P2, in ground frame, G frame. G frame meaning what? Ground frame. SRC procedure for acceleration between C and P2 in ground frame. I draw the line, so SP arrow C, OP arrow P2. Fine. SP arrow C, OP arrow P2. Alright. I draw the line joining C and P2. I give the acceleration of C to P2. But C moves in a straight path with respect to ground at constant speed V. Therefore, acceleration of C with respect to ground is 0. So I give 0 to P2. That is, I don't give anything to P2. Then I write down the sentence. Omega is clockwise. P2 moves in a clockwise circle with center C radius R. So one acceleration I give omega square R to P2 towards center C. And R beta along tangent. But omega is constant as we have determined just now. So beta is d omega by dt, omega is constant. So beta is 0. This term becomes 0. So acceleration of P2 with respect to ground becomes omega square R. Omega is just V by R from pure rolling criteria. The acceleration of P2 with respect to ground becomes omega square R. That is just V square by R square into R. That is V square by R. This is the acceleration of P2 with respect to ground. That is in leftward direction. Okay. So acceleration of P2 with respect to ground is V square by R in leftward direction. Fine. Alright. These are a bit, okay? Now, what I do, I first determine the speed of P2 with respect to ground in using that SRC procedure of velocity. SRC procedure for velocity between C and P2 in G frame. Okay. So SP arrow C, OP arrow C2, P2. I draw the line joining SP and OP, that is C and P2 here. I give the speed of center C to other point P2. So I give V here. Then omega is clockwise. I say the sentence. P2 moves in a clockwise circle with center at C and radius R. So P2 I give a speed omega R. Velocity, but we know from pure rolling criteria that V is just equal to R omega. The velocity of P2 is the vector sum of these two, this and this. Since they are equal and right angle, the net velocity of P2 is root 2V. So velocity of P2 with respect to ground is root 2V. Root 2V, it makes an angle of 45 degree with the rightward direction. Okay. It makes an angle of 45 degree with the rightward direction. Okay. This Vp2G. Fine. Now what I do? This are a bit, okay. Now see one thing. I again draw the approximate shape of trajectory of P2. Again it's a cycloidal path. So path of P2 is again like this. This is the path of P2. Path of point P2. This is the path of point P2. Fine. Alright. See, P2 is here, somewhere here. At this instant. Its velocity is root 2V. We know that velocity of any moving point is always tangential to its trajectory. So as I determined just here, Vp2G is root 2V like this. It makes an angle of 45 degree with the horizontal. So this is the trajectory of P2, this cycloidal path. Here velocity of P2 is root 2v. This makes an angle of 45 degree. And we have just now determined from SRC procedure of acceleration that acceleration of P2 with respect to ground is how much? V square by r towards center C is the acceleration of P2. Now from these two data we can determine the two things. First is the radius of curvature ρ2 at point P2 and tangential acceleration of P2. Okay. So I draw a normal here. This angle is also 90 degree. This is 45. This also 45 degree. This along normal EN2 unit vector along normal to the trajectory, and this is ET2 unit vector along tangent to the trajectory, and this is along unit vector along inward normal to the trajectory. So its normal acceleration can be written in two ways. Root 2v whole square. You know how much is normal acceleration? Normal acceleration is speed square divided by radius. The speed is root 2v as I determined here. So root 2v whole square by radius of curvature is how much? Rho 2. This is the normal acceleration of P2. Okay. And what is the actual acceleration of P2? V square by r leftward. So its normal acceleration is how much? Component of this in this direction, which is V square by r cos 45 degree. V square by r cos 45 degree. Root 2v square becomes 2v square by rho 2 becomes v square by r into 1 by root 2. Now v square cancels out. So rho 2 becomes what? 2r root 2. This is the value of rho 2c. So rho 2 becomes how much? 2r root 2 is the required value of radius of curvature of the curve at point P2. Now we also have to determine the tangential acceleration of P2. Now see, total acceleration of P2 is this much. Its component along this direction is the normal acceleration of P2. Its component along the direction line of action of velocity, that is the tangential acceleration of P2. Now this 45 degree, so this angle will also be 45 degree, opposite angles. So acceleration of P2 along tangent, that is tangential acceleration of P2, AT2, is simply v square by r cos 45 degree. V square by r cos 45 degree. This becomes how much? V square by r root 2. So this is therefore the required answer to the second part of the question. Okay. So radius of curvature of the curve of point P2 is 2r root 2 and tangential acceleration of P2 is v square by r root 2. Okay. So these two answers also have been obtained. Fine. Alright. This also rub it. Okay. Rub this. Okay. Actually, before going ahead, one thing I'll just clarify. For P1, which I wrote the acceleration of P1 2v, I found the speed of P1, SRC 2v. So normal acceleration was P1 was 2v whole square by rho 1, and that was omega square r. Actually, tangential acceleration of P1 doesn't appear that in calculation at all. Just ignore that part. Okay. Is it clear what I've said? Okay. I'll just clarify it at the end. Okay. Now part 3. What is part 3 of the question? Part 3 of the question is this. To find the radius of curvature of trajectory of point P3 and also the tangential acceleration of P3. Again, what do? We find the acceleration of P3 in two different ways. And from that we get rho 3 and 83. Okay. So first what I do, I apply the SRC procedure of acceleration between C and P3 in ground frame. So SRC procedure for acceleration, SRC procedure for acceleration to drum between C and P3 in ground frame. So for that SP arrow selected point is C, OP becomes P3. I draw the line joining SP and OP, that is C and P3. Now I give the acceleration of C to P3. But as I said just now, C is moving along a straight line at a constant speed v with respect to ground. So acceleration of C with respect to ground is 0. So 0, I give 0 to P3. That is, I don't give anything to P3. Now I write down the sentence. Omega is clockwise. P3 moves in a clockwise circle with center at C and radius R. So one expression I give what? Omega square R to P3 towards center C. Another what I give? R beta. For beta is the angular acceleration of drum, which is 0 because omega is constant. So d omega by dt becomes 0. So R beta becomes 0. This term goes away. Now we know that this angle is theta. So this angle will be 90 minus theta. Okay. So acceleration of P3 with respect to ground P3G is simply omega square R directed towards center C, approximately like this, where this angle is theta. Okay. Now what I do is that I find the speed of P3 and its direction of motion also, and then find its normal acceleration another way. Okay. So this side of this one. Okay. Fine. So now what I do, I apply SRC procedure for velocity between C and P3 in ground frame. Entire SRC procedure of velocity as you fully discussed in the previous videos. You go and search it, you'll get it. Okay. They all have been put in the playlist. Okay. So if you go to the playlist, you'll get everything. So SRC procedure for velocity to drum between C and P3 in ground frame, G frame. G frame meaning ground frame. So SP arrow C, OP arrow P3. I draw the line joining C and P3. I give the speed of selected point C to other point P3. That is, I give V. Then I write down the sentence. Omega is clockwise. P3 moves in a clockwise circle with center at C and radius R. So I give R omega to P, normal to this line CP3. By geometry, this angle is also theta. From pure rolling criteria, R omega is also V. So velocity of P3 is the vector sum of these two. Okay, fine. So now what do we get? So this one I will rub it. Okay, this I will rub it. Fine. So velocity of P3 with respect to ground is the vectors of these two, V and V. V square plus 2 V square cos theta. This becomes 2 V square cos theta by 2. And direction, since these two are equal, so Vp3g is the resultant of this. By theory of vector, Vp3g bisects the angle theta between these two vectors. So this angle is theta by 2. This also becomes how much angle? Theta by 2. And value of Vp3g is this much. Fine, alright. Now see, Vp3g becomes 2v cos theta by 2. Now, again what I do, I draw the approximate shape of trajectory of P3. See, P3 is somewhere here. Okay. Again, we know that P3 also moves in a cycloidal path. P3 also moves in a cycloidal path. Okay. So cycloidal path it moves. So if I draw a separate trajectory for P3, it is something like this. Like this. See. This is P3 here. Okay. Fine. So see, this is theta. We have determined the acceleration of P3 with respect to ground, which is simply omega square r. And here velocity of P3 is tangent to the path. But its velocity Vp3 makes angle of theta by 2 with the rightward horizontal. So path of P3 is this one. So Vp3g is this one. Vp3g is something like this, tangent to this cycloidal path. And we know that this angle is how much? Theta by 2. See, theta by 2 here, see, theta by 2. So Vp3g makes angle of theta by 2 with the rightward horizontal. Okay, fine. So Vp3g makes an angle of theta by 2 with the rightward horizontal. Fine, alright. And one more thing. This is the direction of V, R omega, which is V. So this angle is total theta. See, this is V. This makes angle theta. This is theta by 2. And this center here. Now what do you do? I have this one, okay? See this one, see. Now what we have to do, we have to equate the normal expressions of P3. We write down the expression for normal acceleration of P3 in two different ways. See, its path here, VB, this is along tangent. This is the normal. And this is the total acceleration P3, A P3G, which is determined just here. This is how much? Theta. This angle is theta. AP3G, this one. This is AP3G. This one, AP3G is equal to AP3G. This way vertical it makes an angle theta. Theta it makes an angle with the vertical. Okay, fine. So this is the tangent to the path. This is the normal to the path. This is its actual acceleration AP3G. Alright. Suppose the radius of curvature of the curve at P3 is rho 3. Now tell me. See, this V is this one, and this is AP3G is along this direction. So angle between AP3G and this V is 90 degree. This angle is also 90 degree. Okay. So from this you see this angle total is how much? Theta. This is theta by 2. So this angle is also how much? Theta by 2. Alright, fine. This also becomes how much? Tell me. Theta by 2 it becomes. It becomes theta by 2. So, just I'm looking, just slight geometry. And AP3G is how much? Omega square R, that is V square by R. V square by R square into R, V square by R. So, what do we do first? We have to find rho 3. This is the direction normal to the trajectory of P1, P3. So, its acceleration in this direction can be written in two ways. Normal acceleration of P3, A and 3. This can be written in one way as what? Vp3g whole square by rho 3. Vp3g whole square by rho 3. Alright? Vp3g whole square by rho 3. That is equal to A and 3. Okay, fine. Vp3g whole square by rho 3. And that is that can be written another way also. How? That can be written in this way. That can be written another way also. This is the total acceleration of this P3. If you find this angle, then problem is solved. How much will that angle be? This is theta by 2. And this is also right angle. This is theta by 2. So this is also 90 minus theta by 2. See, this is 90. Tangent normal, so 90 degree. Theta by 2, so 90 minus theta by 2. This is 90. This is 90 minus theta by 2. Is it alright? Just check it, okay? See, this is tangent, this is normal. This is 90 degree. This is theta by 2. So 90 minus theta by 2. And this is 90. So this angle becomes how much? Theta by 2 it becomes. Fine. So normal acceleration of P3 is what? This is the AP3G, total acceleration of P3. This is theta by 2. Okay. So this becomes how much? Normal acceleration can be written as what? AP3G into cos of what? Theta by 2. Now Vp3G we have determined just now. 2V cos theta by 2. This is substitute here. So 4V square cos square theta by 2 by rho 3. 4V square, this I substitute here. AP3G is how much? AP3G is simply omega square R, that is V square by R. V square by R cos of theta by 2. Now see, V square goes away. 1 cos theta by 2 also goes away. So rho 3 becomes 4R cos theta by 2. Okay. So this is another answer, the third part of the question. So rho 3 becomes how much? 4R cos theta by 2 is the required value of rho 3. Fine. Alright. Now we have to find the tangential acceleration of P3, 83. This we have to find. This also can be determined in two ways. Okay. So how do you find a tangential acceleration? That is the question. Now see, tangential acceleration can be found in this way. This is the direction of net velocity of P3. This is the total acceleration of P3. Component of AP3G along this direction, that is the tangential acceleration of P3. Okay, fine. This is the total acceleration. This is the tangent. This is the normal component of total acceleration of P3 along its tangent to its path. That is along direction of VP3G. That is the tangential acceleration of P3. Now tell me, how much is this angle? How much is this angle going to be? Tell me. This is how much? This is tangent normal 90 degree. This is theta by 2. 90 plus theta by 2. So this angle becomes how much? 90 degree minus theta by 2 it becomes. This becomes how much? 90 degree minus theta by 2. This is total 180 degree. This is equal to 90 degrees theta by 2. 90 plus theta by 2. This is 90 minus theta by 2. So 83 is how much? Component of AP3G along this direction. That is just equal to AP3G cos of 90 degree minus theta by 2. That is simply, but AP3G is how much? V square by R. V square by R sine of how much? Theta by 2, cos 90 minus theta by 2, sine theta by 2. This is therefore the required answer. Alright, fine. Is it clear? So, tangential acceleration of P3 becomes V square by R sine theta by 2. So, this is the 83. Actually, we can determine 83 by one more way. We can determine 83 by one more way, that is by differentiation method. I love this, okay, fine. '83 by another method. By another method. See, we know the speed of P3 is how much? 2v cos theta by 2. So 83 tangential acceleration is just the derivative of speed. Is it alright? This becomes how much? D by dt of how much? 2v cos theta by 2. Alright? So this becomes equal to 2v d by dt of what? Cos theta by 2. This becomes 2v d by d theta of what? Cos theta by 2 into I'll differentiate this d by d theta into d theta by dt is simply omega. Omega is the angular velocity of the drum. Okay, fine. So this is a bit now, this one, okay? So 83 becomes how much? Becomes 2v d by d theta of cos theta by 2 minus 1 by 2 sin theta by 2 into omega. 2 cancels out. Omega becomes v by r from pure Rolling criteria. So minus v square by r sin theta by 2. See, if you take the magnitude, here what we obtained A3 was just the magnitude of 83, this much. And this we have obtained the actual tangential acceleration with sine. See, minus means that speed is decreasing at that instant. It should be, because AP3G makes an angle of obtuse angle with its velocity vector. So if we know that total acceleration of a moving point makes an obtuse angle with its velocity vector, then its tangential acceleration should be negative. So that's why it's getting a negative sign here. Here we obtained the magnitude, so they are both correct. So 83 has also been obtained. Alright. And rho 3 is also determined here. Is it alright? Fine. One last point I'll say. See, if you use this result to determine rho 1, rho 2, we can get for rho 1, how much theta is 0 degree. So how much for P1, P1. So rho 1 is how much? 4r cos 0 by 2. 4r cos 0 by 2. Cos 0 by 2 is cos 0, that is 1. So 4r is just 4r. Answer which you obtained in beginning of this problem. For P2, how much theta is 90 degree. How much rho 2 will be? Rho 2 will be 4r 4r cos of 90 degree by 2. So cos 45 degree 1 by root 2. 2 root 2. Same answer which you obtained. Okay. And tangential expression is how much? V square by r sin theta by 2. If you use this result for P1, P2, we are going to get 80 for these 2 points also. These are a bit fine. And for P1, what is AT1 going to be? V square by r sin of theta by 2, 0 by 2. Sin 0 by 2 is sin 0. Sin 0 is 0. So AT1 is 0, which you obtained there also. Actually, there where I obtained AT1, I wrote as like this. D by dt of 2v. This we can't say. This is not correct. This you just ignore, okay? I'm just repeating it here. I should not have written it that way. But it was discovered it just now. So just remember it. I'm clarifying it here. At AT1 which I did for that P1, I derivated this term. This is not correct. That's wrong. First you have to get expression, then you can put the value of theta. You cannot put the value of theta first and then differentiate. No. So that's just, I'll clarify it, okay? I did not clarify that, just skipped it. I just missed it, okay? This I've clarified it here. And so tangential expression becomes 0. And for P2, theta becomes how much? 45 degree. So tangential expression 82 becomes how much? It becomes V square by r sin of 90 by 2, sin 45 degree. 1 by root 2. The same answer which you obtained there also. Alright, fine. This was the 30th video on rigid body kinematics. This is the 30th video on rigid body kinematics. Okay. So if you go through it properly, you will understand it. If you have any doubt in the understanding this contents of video, you write in the comment box. Okay. I'll clarify it. And you go through it properly, you don't have to go anywhere else. It's more than sufficient. It's sufficient for a mains and advanced both. If you understand it fully, you just take a problem from any other source. I'm sure you'll be able to solve most of them. In case you have some problem, you write it in the comment box. I will clarify it. Okay. So I close it here.